December 13th at 10:30 to 12:30, right here. "60 multiple choice questions." Same style, same things. You'll sit one apart. You can have a cheat sheet. You can use your calculator. And yes, I split the 60 questions up fairly evenly between all of our material. So no one unit or section is weighted more than the other intentionally. There's a lot of overlap you can see. You've noticed throughout the semester. What else? We will not have the opportunity to do a makeup final exam because not only are classes over, finals are almost over. So that'll be it, that day of class. There'll still be bubble sheets circling your answers. When you're done, you can leave. Your final will be over. And you might, if it's your choice, you'll never have to see me again. I don't know. Sad. Okay. Any other questions about the logistics of the final? What are you guys going to do to study and prepare for it? Study groups. I highly encourage that, especially if any of this seemed muddy to you or you're not proud of your individual exam scores. Remember how I said when you try to explain it to someone else, sometimes he can tell you the exact same thing I told you, but you'll get it. I'm not offended, so take advantage of that if you can. Yeah?
Look at the web works and look at the notes, like your art.
Oh, yeah, I've had you do lots of problems. Yeah, for a reason, to get you thinking about this and prepare. So yeah, and I have all my solutions posted. They're all there for you. Good. What else? That's it, huh? The book. Thank you. How many liked the book? Now, let me preface this because I'm realistic here. Those of you that bought a book and actually used the book, raise your hands. All right, keep your hands up. Of those hands, put them down if you didn't like the book. That's pretty. I hardly saw any. There might have been one or two. Okay. He explains things really well, and we talk similar. But if you don't get it all by me, he can explain it a slightly different way. And definitely more in grimy detail for you to just go over and over again. So yes, I've referred to the book often. What else? You can. I've had very few people come and talk to me or email me questions all semester. Has anybody ever gone to see the TA? That's what he told me. So yeah, that works. There's example problems in the text also, checkpoint questions. There's practice problems at the end of each chapter. And the odd answers are in the back of the book. The answers to the odd problems. Not the weird problems, the odd numbered. Okay. That's just stuff in the class. There's a lot, you can go outside and Google and tutors and all that stuff too. But okay, good. Good. I'm going to start with you guys. Do you have any dying questions you want to begin with? Because I've been encouraging you to think about this stuff. If it hits you, raise your hand, okay? Come Wednesday. 2 with them. So I have the final. It's right here. All right. Highest bidder. No. And yes, I know this is recorded. I'm joking. It's just kidding. But I'll look at this because it'll be more pertinent. I also I just went through my notes. I took like a half an hour. Went through my notes. And chapter 1 was called About Science. And seriously, it wasn't even a half hour. Here's chapter 1. I looked through it. Okay, what was important? Oh yeah, scientific method. I just wrote down the key things. Facts, laws, theories, hypothesis. Remember all those way back when? Those were important then. Those are our key words that were defined at the end of your chapter. We did them. I asked you a few questions about those on the test. I think it was on theory. Is that the one I chose this semester? So I did a similar game with each chapter. We could just go through that way until it prompts questions for you. But unfortunately, we will not have time to just hit everything again, even if I spend 30 seconds on it. So I would prefer to address issues that you had more problems with to be more efficient. So if it seems like I'm whizzing through this, I'm going to assume you're okay with that. You'll stop me, won't you? Are you brave enough by now? Have we made this a comfortable enough atmosphere? Okay. Well, on that, do you know what all those are? Facts and theories and hypotheses and laws? Can they change? Yeah. Sure. Theory. Remember we started with theory, and it's like, oh, that's a lot of non-scientists think scientific theories are like, well, they're not quite sure yet. It's just a theory. It's a working theory. Theories were actually the highest one. Remember, it was kind of like a big synthesis of other laws and facts and principles tested over lots and lots of time, like the special theory of relativity. The theory to a scientist is like pretty dang solid. However, as we gain more information and learn new things, different experiments, we'll adjust. A good scientist will stay open and adjust. Those that don't listen to you and take new ideas, if any of you decide to go into the sciences, don't let anybody tell you that, oh, you're dumb, you can't handle this, oh, that's an absurd theory, blah, blah. If we don't know yet, then how can they say you don't know? It's good to stay open. Okay, chapter 2. That was Newton's first law of motion. Chapter 2. I'll sum it up by inertia. We got the 3 Newton's laws. See, chapter 4 was second law. And chapter 5 was the third law. And yep, you better know what those are. We've used them all semester. Who can quote them right now? Bet somebody can, without having to look at your note. What's the first law? It has to do with inertia. What's inertia? It's a property of matter. Yeah, resistance to changing motion. So things at rest want to resist moving. That's why they stay at rest. Things that are already in motion want to resist going faster, slower, or stopping. So things in motion will stay in motion. That's inertia, that property of matter that keeps them doing that. They do it all on their own. Remember, you chuck an apple out in space, whoosh, it'll just go in a straight line at a constant velocity forever, unless it's acted on by a force. That's Newton's second law. What does that force do to it? Say it again. Yeah, that's right. That one summed up by this guide to our thinking. F equals ma. You apply a force to a mass that's trying to resist you. That's how you get it to change its motion. Change in motion, acceleration. Acceleration is defined as what? Right, a change in velocity with a change in time, over time. What's velocity? What's it a change of? Position. I'll use x as a represent position. It's a change in position. It's how fast you change your position. You go from here to there. X representing a change in position. If you're here at point x1 and you move to point x2, there's a distance. We sum that up usually later in the semester, just distance over time. You moved some distance, technically a displacement, but whatever. We don't care. So that change in motion is referring to acceleration. If you accelerate, then your velocity changes. And the only way for that to happen is to overcome its inertia by applying a force. And then we added other forces. What if you have a whole bunch of forces pushing on the same object? Which one wins? The biggest one? They all contribute, so you have to consider all of them, don't you? It's that total force, or we called it something else. Net force. And yeah, you know this. If I push on this table this way, at the same time Tayson pushes it this way, then we have to add the forces together. And if I push at the exact same magnitude of force that he pushes, but in opposite directions, does the table move? No. The net force would be 0. If the net force is 0, what's the net acceleration? 0. If the net acceleration is 0, what's its change in velocity? 0. We did a lot of that, but that was a long time ago now, wasn't it? Bless you. If the net force is 0, I wouldn't say everything else is 0. If the net force is 0, the net acceleration is 0. Has to be. Newton's second law. F equals ma. And if the net acceleration is 0, then there's no net change in velocity. No change in velocity. So it could still be moving. Give me an example where the net force is 0, but the object is still moving with a constant velocity.
Something that would never stop moving then because it has an acceleration.
That's right, it would never stop moving. But what would be an example? What? A hover cart. Ah, yes, we did that where we eliminated friction. So if it just kept moving at a constant velocity. Yeah, there's no net force on it. Horizontally, there's actually no force on it, ideally. If you don't push it, and there's no friction to slow it down, how does it keep moving?
There's still acceleration. Acceleration isn't being stopped.
If there's no net force, there can't be an acceleration. That hover disk we had, it put air out here. And so there's ideally no friction. So there's nothing trying to slow it down, decelerate it. Once I kick it, it just keeps moving. After I kick it, there's no push either. Nothing is pushing it. So horizontally, in the x direction, there's no net force. So there's no acceleration in the net direction, in the x direction. It doesn't change its velocity in the x direction. But it still has a velocity. The velocity is not 0. It's still moving. What keeps it moving? Because there's nothing pushing it. Thank you. Inertia. That's that property of matter, that things in motion want to stay in motion unless acted on by a net force is more technically accurate. If there's no net force on it, it'll just keep doing what it was doing, whether that was staying put or moving. Your car. We did a lot with a car. You accelerate. You know you're putting energy in. And you're maintaining 75 miles an hour down the highway. Is your velocity changing? Nope. So what else do you know? Not only is your acceleration not changing, it is... It's 0. If your velocity is not changing, then the acceleration has to be 0. Yes, that's not changing. And if the acceleration is 0, the net force is 0. But this time we know there's forces acting on the car. But they must cancel. The net effect is 0. What are those two forces horizontally in this case? Friction, trying to slow your car down. We'll lump air resistance into that.
It's the road as well as your tires.
Right, and the ground trying to propel your car forward on the tires, yeah. So the push and the friction. But they're balanced. When they're balanced, you don't change your velocity. What if you accelerate more than friction? The force is greater than friction. What happens? You speed up. You accelerate. There is now a net force. There's a change in velocity. You go faster. Then you ease off the gas pedal, and the two forces balance again, and you maintain that new velocity. So there are some questions on the test about this. Balancing some forces, this relationship, that property of inertia, property of matter called inertia. Do you remember how to calculate your weight? Let's make it easier. Let's do it different, more realistically. You guys all jump on a scale and get your weight. Who's not embarrassed to give me your weight? I've given you mine all semester, so. 200 pounds, all right. Pounds. Now that's not our standard unit. But we'll work with it. What is that? Which of these is that? F, M, or A?
Well, you have to change it to mass.
You're right. I heard somebody say it's F. That's a force. That's your weight. And weight is a force. It's the force at which the Earth pulls down on you. It's trying to accelerate your mass, MA, at that rate, or that amount, 200 pounds. A force, weight, what is it? It's mass times acceleration. What's the rate of acceleration here on Earth? Right, mg. And that value? Yeah, it's about 10 meters per second squared, or meters per second per second. It changes 10 meters per second every second. See, change in velocity. So yes, we would need to convert this to newtons first. Newton is the standard unit for that, for weight, force. So if you divide this number by the acceleration of gravity, you're just left with the mass. Yeah, I should know this. I really should. I probably have it written down somewhere. But the conversion factor between pounds and newtons, it's either 4.54 or 1 over that. Or if somebody Googles it before I get there. If we did that, yes, 200 divided by 10 would give us the mass, but I wouldn't know what the units are. They'd be pounds, meters, it'd be something funky. What's the unit for mass, the standard unit? Kilogram. If you want it to come out in the standard unit, then you got to start with standard units. So we would convert 200 pounds to newtons first. And I don't remember what that conversion factor is. Has anybody found it while I was talking by chance? Hey, sure it's in the book. There it is. 1 kilogram is 2.205 pounds. That's our conversion factor. Wait. That's what it puts in the back of the book. It's not the one I wanted. There's the other one. 1 pound is 4.448 newtons. This is a good exercise. This is the one I wanted, because these are both forces. So If 200 pound, 1 pound is about 4.5 newtons, what's 200 pounds in newtons? We multiply it by this number. Multiply, not divide. If 1 pound is about 4 newtons, then 200, this should be 8 or 900. 889. We'll just call it 890 newtons. There we go. Now you can always convert your weight to newtons. Yes? No. But people did and still get mass and weight confused. So I thought this would be a good review. So now we can do this. We got 890 newtons equals mass times gravity. And gravity is 10 meters per second per second. The acceleration due to gravity. So your mass is 890 divided by 10. This one you might have to do. 89 kilograms. There you go. So whoever said they were 200 pounds, you are made up of 89 kilograms of matter. Because most people don't know how much mass they have. Now you could go figure it out for yourself or anybody.
Why is it kilograms and not newtons?
Because to emphasize that Newton and pounds are units of force. Weight is a force in newtons. Mass is not force, it's in kilograms. So that I'd get the standard unit of kilograms. If this were in pounds, I don't know what this unit would have come out to be. Are your standard units? Yeah. So if you plug in kilograms, if say you're 70 kilograms, that's your mass. 70 kilograms times the acceleration due to gravity in standard units, 10. 70 times 10 is 700. That's our weight. What's the unit for weight? It's a force. Newtons. So you're 700 newtons. If you want to go back to pounds, you use this conversion factor. But realize pounds and newtons are both units for force. This is just not the standard unit. Now you're going to see this a lot. This one. It's even in your book. I saw it first. I want to emphasize. See how it converts mass to weight? Mass and weight are not the same thing. What this conversion does, it's a shortcut for what we just did. It uses Newton's second law and did that for you. If you want to, it already divided by the acceleration to get it for you. But a lot of people, because this is out there on the web and in textbooks, they think kilograms and pounds are the same thing. No, no, no. Kilograms is for mass, which is different than pounds and force. So if you ever see that, I want you to remember back to Newton's second law and how they're related. Yes? They both measure force, pounds and newtons. It's just like meters per second versus miles per hour. They both measure velocity. Or inches measures distance versus centimeters. There's just a different unit for the same thing.
If you had like a scale though in like England, do they measure kilograms on like the scale?
Most scales do not give you your mass directly. They give you your weight. Because it's measuring your weight. It's how hard you push down on it.
Do they use pounds in like other countries?
The United States is the slowest. Most other non-third world countries have converted to the metric system in the standard units. The United States is holding strong to the old school. But if you look up a conversion factor, it shouldn't slow you down at all. Since most scales in the United States are still pounds, that's why I wanted to share this with you. So let's see other questions. Remember, would balance those forces. We had a pulley. How hard do you have to pull on this to balance this mass if you're over on this side? Yeah, let's say you just lift it up and hold it. How much force are you applying? It's got to be equal to the block's weight, because this over here is getting pulled down with that force of its weight. So you have to counter it and pull with that same force. You're balancing forces. Then if it's balanced right there, what's the net force? What's the net acceleration? 0, 0, because it's not moving. To get it to go up, what do you have to do? You got to apply more. This has to be a little bigger than that to have the net force up over here a little bit. Do you see that? So it'll accelerate and get up to a speed. Could you then reduce your force back down to mg? Sure you could. What would happen then? You get it moving, then you reduce your force down to mg. What happens now? Does it stop? What's the net force now? 0. So what's the net acceleration? 0. What's the change in velocity? 0. Wasn't it already moving? It would just keep raising up at the same speed you got it up to. See, there's another example where the net force is 0, but it's still moving. Did you follow that? Anybody? So yes, you have to apply greater force to get it moving, to change its motion in the first place. But you don't have to keep applying that greater force to keep it moving. Otherwise, it'll just accelerate and go faster and faster and faster and faster up the pulley. You could, but it's not necessary. Yes?
Okay, so there's a problem that said that the max that the person on the other end could pull is his own weight.
Oh, I remember that question. Yeah.
I swear someone could pull more than that.
Okay, let's see. If this person pulled with his weight, it said that was the maximum. What would happen? Let's just picture this. You have a rope here. Yeah, I bet you could too. Pull greater than your own weight. You'd raise yourself up. Let's say there's just a rope hanging here, and you pull on it. If you're pulling down with a certain force, it's got to be pulling up with a certain force, right? Well, let me do it this way. Earth is pulling you down with mg, your weight. We'll make it big M. If you pull up with that same, nothing happens, right? Net force 0. You don't move. But yeah, if you pull even harder, now this is bigger. You see the net force now? It's up. And you actually lift off the ground. That's how you climb a rope.
So there's no way that you could ground yourself in order to pull the weight higher.
There you go. Now he's thinking. There you go. Anchor your feet to the ground or something. And now pull really hard. Now you could pull greater. But if you're freestanding, you start to pull up to your weight, but as soon as you go more than your weight, you lift off the ground, and it's kind of counterproductive. You can't pull in. It doesn't help lift that mass on the other side of the pulley. Good question. Which is why I put it in the homework. What's the difference between speed and velocity? Yeah, speed is a scalar. It's only magnitude. Velocity is a vector. Speed with a direction. A magnitude and a direction. So if you change your direction, you're changing your velocity. And if you're changing your velocity, what's the net acceleration? If you're changing your velocity, what's the net acceleration? The acceleration is the same as the change in velocity. It's not 0. which means there must be some net force causing that. On your car, remember, there were 3 ways you could change your velocity on a car. Speed, the gas pedal, speed up. Brake pedal, slow down. Steering wheel, change your direction. They would all change your velocity and require a force to do that acceleration. How about throwing an object up? That one gave some folks some problems. Yes, I know, those of you that are going, wow, we're spending a lot of time at the beginning stuff. How many are feeling good, though, because that I'm doing this? We got a whole other class, but this is the longest to go, so I figured this is the most you forgot. Obviously, we don't have to review waves and stuff as much. All right, what's the acceleration on this apple? Who said 10? Raise your hand, be brave. What's trying to accelerate it at 10? Gravity. Is it successful? Because I'm pushing back up. What's the net force? 0. So technically, I should ask, what's the net acceleration on this apple? 0. There you go. All right, as soon as I let go of it, what's its acceleration, net acceleration, on the way up? More than 10? As soon as I let go of it, like right now. So it's accelerating up at more than 10. Who agrees with that? Who disagrees? What are you thinking? Yeah. Let's draw a free body diagram. I encouraged you to draw free body diagrams. Here's your apple. All right, it's on its way up. It has a velocity because it's going up, right? All right, what are the forces acting on it? Gravity. mg. That's its weight. That's the force. And somebody said air resistance, which would slow it down a little bit too. Air resistance. Anything else? But wait, it's moving up. Is nothing pushing it up? Initially, I moved it up, but once it leaves my hand is no longer acting on it. Inertia is what's trying to keep it moving at that speed until a force acts on it. These two. So that force causes an acceleration, and it changes its velocity. It slows down. So ideally, its net acceleration would be, how would you compare it to 10 meters per second squared? Not ideal. Realistically, the way it's drawn here, what would be the net acceleration on the way up? What's this trying to accelerate it down at? 10. And this? A little more. It's pretty insignificant, but realistically, it's there. And so, yeah, it's actually trying to accelerate slightly more than 10 meters per second squared because of air resistance. Without air resistance, what is it? 10. What is its net acceleration at the top? Right there at the top when its motion stops. What's its net acceleration? What's its velocity at the top? What's its acceleration at the top? 10. It's still being accelerated down by gravity. So remember, there's an example where you can still have an acceleration, a net force acting on you, and not be moving. It's when you change direction. Remember, the force and your motion can oppose. That's your car. When you brake, you guys just told me, you're moving along like this and you slam on the brakes. Do you just immediately start moving the other way? No, you're still moving forward in the positive direction, but you're decreasing your speed. You're slowing down, and then you stop. The acceleration, the force is that way, but your motion was that way. What if it was a cart? Somebody could just be pushing on you. The apple is rolling, you're in the car, and you just start pushing on it. Ooh, you slow it down, stop, and then get it going back the other way. You can actually change its direction. So that's no different. Right there, it stops for a moment and you push back. That's no different than this. It stops right there and comes back. So I'm just trying to reemphasize and remind you that at the top, the acceleration is still 10 meters per second squared.
So acceleration is always 10 if there's no air resistance.
If there's no air resistance, yeah, if you're just under the action of gravity, we call that free fall. And gravity's always on. You can't turn it off. So it's trying to accelerate things down at 10 meters per second squared, always. What's its acceleration then on the way down? Now. 10. It's going to make it go faster and faster now, instead of slower and slower. But acceleration is constant for the Earth's gravity. Is that helping? Queries? Yes, Carl.
You could just tell me to go look that myself, but what are the chapters
That's why we're here.
looked up so I can look at them in my book tonight and then on Wednesday?
This was all you mean for everything or what we're just doing?
Yeah, like all the, just like the numbers.
Oh, yeah. I can do that. It's in WebAssign too. It's on the calendar. If you just look at exam 1, here's the chapters. Exam 2, here's the chapters. But here we go. 1 through 5 was our first units. And we've actually been talking about all of that. That was about science, Newton's laws, and linear motion. Chapter 3 was linear motion with all this speed, vector, acceleration stuff. Then we had exam 1. Then we did 6, 7, 10, and 35. That was momentum, energy, projectile motion, where we threw things in 2 directions, and special relativity. Momentum, energy, projectile motion, and relativity. Obviously, we'll do a lot. We'll start moving into that, because that was the second oldest thing. Then we did things that flow. Liquids was 13. Gases was 14. Jumped gears a little bit to electrostatics and electric current, charges that flow and move. So liquids, gases, electrostatics and charges, electric current was circuits, series and parallel. And last but not least, waves, 19, 20, 26, 27, and 29. We started with vibrations and waves in general, related it to sound. Then we looked at light. My favorite, color mixing. And then light waves at the end with diffraction and polarization in chapter 29. Those are the chapters we've gone through this whole semester. We just had a real good review of the first ones. Let's see. Oh, while we're on this, did that. This one. Do you remember it? My example is often you drop a rock down a well, or spit gum off the Golden Gate Bridge. See how long it takes to fall. That's the time it takes to fall. What made it fall? The acceleration due to gravity. That tells you how far it went. This is the distance something will go if it's accelerated at that rate for a certain amount of time. That's one formula people tend to forget about. Remember that squared term, how it got faster and faster? We had a cart that went constant velocity. If it goes constant velocity all the time, what's its acceleration? 0. If its velocity is not changing, boom, you know the acceleration is 0. And if the acceleration is 0, what's the net force? 0. After 1 second, let's say it goes here. How far will it go in the second second? Same distance. Third second. See, its position is changing, isn't it? Well, that's what velocity is. Velocity is a change in position, distance over time. You can figure out how far it goes. If it changes its velocity, what will happen to the distance? That's right. Now, it's not constant. Let's say the acceleration is constant. Constant. And we know it's not 0 because the velocity is now changing. It's going to go faster and faster. So yeah, if the first second it gets here, the second second, well, now it's going even faster, so it'll get even further. And now it's going even faster than that. It'll end up over here, right? So the spacing changes. How much will it change its velocity each second? Let's make it easy. Let's say it's falling. If the acceleration is gravity, 10 meters per second squared, now it's like this way, right? It's falling. How much does its velocity change each second? 10 meters per second. This is 10 meters per second every second. Remember we dropped things? You might review that chart in your notes or the book. If this is time 0, at time 1, how fast is it going now? 10 meters per second. It just changed 10 meters per second, so it's got to be up to 10 meters per second. How fast will it be going after the second second? I heard 10, 15, and 20. I heard more 20s. 20. The change is 10. It'll change 10 meters per second every second. If it starts at 10 here and changes by 10, it'll get up to 20 after the second second. And at the third second, 30 meters per second. You want to know how far it fell each second? Here you go. That'll tell you where it's at. That has the squared term, so most of you pulled out your calculators for that. But how do you feel about the relationship between speed, velocity, position, and acceleration? Decent. Well, you got a week to go back and check. Come Wednesday. What's momentum then? Chapter 6. What's momentum? It was a lowercase p. Yeah, it was the product of mass times velocity. It's inertia in motion. Yeah, and remember, you know this, if you got something big moving, you know it's going to be hard to stop. Something that's moving wants to stay moving unless you push on it to make it stop. Well, the bigger its mass, the more momentum it has coming in. You're going to have to apply a bigger force to stop it. You know that. What if it's coming in faster? You know you're going to have to push harder to make it stop because it's coming in with more momentum. But again, it will not change that velocity. It won't slow down or speed up for that matter unless what happens? You apply a force to make it change its velocity. So we apply that force for a certain amount of time because it takes time to apply a force. That causes the change in momentum. The momentum will change if you apply a force for a certain amount of time because it'll change that velocity. And we had a name for this. Impulse. A big I. Again, I want to emphasize, impulse is not the same thing as momentum. Impulse is the change in momentum. Just like velocity and acceleration aren't the same thing. Acceleration is the change in velocity. Impulse is definitely the change in momentum. It's going to cause a change in that MV. You can change the mass, like a rocket losing fuel, or most things where it just speeds up or slows down. It changes that. And you know what caused the change? It was a force for a certain time. That impulse makes the change in momentum. Then we started colliding things and conserving momentum and energy. I'll stop there, and remember that's where I'll start next time. All right, see you Wednesday.